Just 1 second. Let me know firstly which if you have questions, TK, if you want to go through a topic. Well, about the board sharing, I couldn't actually figure out how to share that board link. So what I can do is, लेकिन पहले वो बता दो if you have questions, TK.
Sir, I have a question.
TK, which paper?
Sir, it's from QP43, May-June 2019.
Yeah, 1 second. 4-3 and somewhere 19, right? So which question?
Sir, question number 8.
Okay, question number 8. So इसके बाद I'll explain gas liquid chromatography very quickly as well. Question number 8 first. That's question number 5, 7. 1 second, 8. Okay, so this entire question, right? We can go through this question. First thing, you have to prove that it's got 5 carbon atoms. All you have to do is you've got a formula for that, which is, okay, how do you figure out the number of carbon atoms? It's 100 over 1.1 into the m+1 peak, which is 1.25 over here. So it's 1.25 divided by the m peak, which is 22.65. So you try and calculate this, and it will hopefully come out to be 5 or something close to 5. Next one, you've got the mass spectrum has a peak at mass to charge value of 57. Complete the equation to show how the fragmentation of X to produce this peak. So you need to show the fragmentation in this case. Now, you've got C15, C5H10 and O2. Okay, that is what you have. And they've given us no other information about the structure of the molecule. So what could be 57? That it has a mass of 57. So it might have 4 carbon atoms. Just 1 second. So 1 second. This one. So 57. What is the total mass of this thing? It's C5H10O2. So that's what's the total mass of this thing? That's 5 carbon atoms. That's 12 into 5. That's 60. Plus 10 hydrogens. Plus 2 oxygens. That's 32. So the total mass comes out to be 70 plus 32, 102, right? So one of the particle, when it gets broken down into pieces, one of the particles has a mass of 57. So what could that be? That could be, I'm suspecting that this molecule is either a carboxylic acid. They didn't tell us, but I know that COOH has a mass of 45. If I add how much to it, I can add, how can you get 15? CH3 is 15. CH2 is 14. CH3. So what is, sorry, that's CH3. You can have another CH2 that's, so what is the total at the moment right now? It's 15 plus 12. Does it even have a calculator with them? As 15 plus 12 plus 12, that's 24 plus 15, that's 39. In 39, if I add another CH2 in 39, so if I add another CH2, that's 51, right?
That's 57.
This is 57.
246 plus 39 plus 48. 9 plus 48.
That is 57.
Yeah.
Okay, that's. Ajay, 1 second. Ajay, so that is 57, right?
Yeah.
Okay, so this is this part, right? So what is left? You just subtract and always put a positive charge when you're trying to figure out what your fragment is. Put a positive charge on that. So it was just trial and error. The other part, subtract these atoms from this molecule. So you're left with 1 carbon atom, right?
Mhm.
And how many hydrogens? That's 3 plus 2. That's 6 plus 3, 9, right? So you're just left with 1 H and 2 oxygens, right?
Yes.
So 2 oxygens, right? So that's put a positive charge on that. So these are the 2 fragments. That's 57, and this is the rest. If you subtract 102 and 57, okay. Now the next part is about and remember, fragments. It's all about guesswork. It's not. There's no science behind it. You just have to make an intelligent guess. That 57 is a small piece of this bigger molecule. That's it. Moving to the next one, you've got state the use of TMS and Cdclc in NMR spectroscopy. Now, this one, they're not going to ask you any further explanation. It's just a one-line statement that you have to remember about TMS and also about Cdclc. First thing, TMS is used as a reference. It's used as a reference. While now the reason you need a reference is that you've got all sorts of hydrogen protons and they're all resonating at different frequencies. Like if I have a molecule, even the explanation, no one is going to ask you about that. So if I have a molecule like ethanoic acid, it's got these 2 hydrogens. They're resonating. One of them is resonating at whatever the chemical shift is. The other one, these 3 hydrogens are in the same chemical environment, so they will be resonating together. Now you've got 2 sets of hydrogens. There's frequency F1 and there's frequency F2. The TMS is a molecule that is used as a reference. This is tetramethylsilane. It's a silicon with, you should at least know what the structure is, because maybe they don't use the word TMS. Maybe they show you the shape of the molecule. So this is what TMS looks like. So this is just used as a reference for comparing the frequencies of these protons, and these protons are compared to this. That's how chemical shifts are calculated. So that's about it. And what is Cdclc? When you're doing NMR spectroscopy, you don't use water as a solvent. If it would be pointless to put ethanoic acid in water, because water has hydrogen protons as well. So they would be resonating as well. So you would be getting many different peaks because of the water. So you want a solvent that does not resonate, which is why you use deuterated solvents. And Cdcl3 is one example of that. So that's used as a solvent. Because if you mix ethanoic acid wouldn't be in vacuum, it would be dissolved in something. So if you mix it in Cdcl3, this solvent will not resonate because it doesn't have a hydrogen proton. It's got the other isotope of hydrogen which does not resonate. Okay. And moving to the next part. Just 1 second. Okay, I'll do this after this one. Now moving to the next part, you've got moving to the next part, we've got a proton NMR spectrum of compound X, C5H10O2, and is shown. So the NMR spectrum is shown by considering both the relative peak area and the chemical shift values. Use the data booklet to reduce the part of the molecule that produces the peak at delta 2.2. First thing, you've got 3 protons resonating in this environment. That's CH3. Forget the parts. You can do this directly. That's CH3. We don't know what type of CH3 that is. but I know that there are 3 protons in the same environment. That means 3 hydrogens in the same environment. This is CH3 as well. I've got 2 hydrogens in the same environment. That's CH2. And I've got 2 protons in the same environment. That's probably going to be CH2 as well. So I've got, I'll answer this after this one. So I've got all these protons. I just need to put them together. First thing, this is a triplet peak, right? So if it's a triplet peak, what does that suggest? What's the neighborhood if it's a triplet peak? What is the CH3 connected to?
CH2.
Okay, so when you have a triplet peak, that means you got 2 hydrogens on the next door carbon atom. So that's CH2. Okay, the N+1 rule. This one is a singlet. So what does a singlet mean? Who's next door? Do you have any protons next door?
No.
Okay, so that means no hydrogen protons in its neighborhood. So then you have quadruplet. The next one, you've got a quadruplet peak. That means the how many hydrogen protons do you have next door? That's going to be. Okay, so that means there must be a CH3, because if you get a quadruplet peak, you got 3 hydrogens next door, and again a singlet peak. So that means no H protons next door, right? So then the next part is you've got to figure out. So I know that CH3 is next to CH2. I mean, I know I figured out this part, right?
Yeah.
So I figured out that the CH3 is next to CH2 and the CH2 is next to CH3. So I figured out at least this part of the structure. I also know that there is a CH3. Remember, the CH3 is always at the end. So I know that there is a CH3 at the end. I don't know what's next to it. I know that it doesn't have hydrogen protons, right? I don't know what's next to it. I also know that there is a CH2, but no idea what's next to it. So I'll open the data booklet now to figure out. This one was easy. I knew by looking at the splitting pattern, I knew what's next door, right? But anyways, I'll now open the data booklet and I'll look for the table now. And your table for this one. So I got a CH3 which has no hydrogens next door to it, right? So I'm focusing on this one, and it's resonating at 2.2. Whatever this is, I think this is 2.2. So it's resonating at 2.2. So let's so what does the data booklet tell you? What kind of CH3 is that? So that's a CH3 that's next to C bond O. That is the type of CH3 that resonates at 2.2. There's another one which resonates in the same range, but that's CH3 next to an aromatic benzene ring. We don't have a benzene in this case, so that's out of the question. So we'll go back and I figured out this one is next to what? It's next to a C double bond O. So this CH3 over here, it's got a C double bond O which is next to it. And the final thing is I'm left with this CH2 over here. And I'm also left with one oxygen as well, because there were 2 oxygens, right? So I figured out this end of the molecule and I figured out the other end of the molecule. The only part missing is where do I put the CH2? And there's one oxygen that's missing as well. So they must be right in the middle over here. That's the only place that they have, because I figured out both ends. The only missing piece is this one. So like a puzzle, this missing piece is going to be put right in the middle over here. But to keep it a singlet peak, what I'll do is there's a missing oxygen as well. I'll put the oxygen here and I'll put the CH2 in the middle, right in the middle, because it's a singlet peak. It should not be next to CH2. It should not be next to any hydrogens, because it's a singlet peak. So that is what my answer is going to be. I mean, that was the only tricky part, the end part, right? That you had to figure out. So I'll just quickly go through this one. CH3 next to CH2 because it's a triplet peak. This is a CH2 next to CH3. So I figured out these two are together. There's a CH3. It has a resonance at 2.2. So that means it's got a Cdl bond O next to it. So I got a CH3 next to a Cdl bond O. The only missing part is where do you put the CH2 that's going to come right in the middle and should be away from that CH2 because otherwise they would be splitting. So is this clear?
Yes, sir.
And the rest you can probably figure out. They actually gave you this when reacted with, there's an iodoform test happening as well. So when you have an iodoform test, when you have a CH3 right next to a Cdl bond O, that's when you're going to have an iodoform test. The CH3 is going to break off, and this CH3 will form a yellow precipitate of CHI3. So that is what the iodoform test states. And as I said, the next part is, it also states that compound W is an ester with the molecular formula C5H10O2. And so there's this compound W. I don't know what W is. We were talking about compound X. There was no mention of W anywhere in the question. So W is something totally different. So this is the next part of the question. So I've got a compound W. It's an ester, and it also has the same formula. And the proton NMR spectrum of W contains only 2 peaks. And the relative area of these 2 peaks are in the ratio 9:1. So you got 2 peaks in the NMR spectrum. One is at, let's say, frequency F1. The other one is at frequency F2. One of them has a relative height of 9, and the other one has a relative height of 1. Now, whenever you have a relative height of 9, the only way you can have 9 protons is you could have 3 CH3s, right? And all 3 of them are in exactly the same environment. So how can all 3 CH3s have the same environment? The structure would be something like this. Because that's the only way all 3 CH3s are in exactly the same environment. 9 protons resonating at the same frequency. So what are you left with? You're left with, there's 1 hydrogen in a different environment. So I'm left with 1 carbon. So all I need to figure out is, it's an ester as well, right? So I need to make an ester link. So this would be Cdl bond O, and there's going to be 1 H, right? So that's about it. That's the only ester that's possible. So 1 hydrogen in a different environment and 9 hydrogens in the same environment. So the ester will have hydrogen protons with the relative height of 9:1. And then there's another compound, which is V, which is a carboxylic acid, which contains a chiral center. It also has the molecule. So there's another isomer. Another thing that is not given above, has nothing to do with the above, but it has the same formula. Explain what is meant by the term chiral center. So carbon that's bonded to 4 different groups or atoms, groups of atoms. The other thing is it's got the molecular formula. I need to make a chiral. It's a carboxylic acid. That's the only information, and it's chiral. So it's a carboxylic acid, which is chiral. So I'm going to focus on the chirality part. All 4 groups, remember C5, H10, and O2. So all 4 groups got to be different. So I got to make it a carboxylic acid. They told me to. So carboxylic acid goes over here. All 4 sides must be different. So maybe put an H over here. I need to make this chiral, all 4 groups different. So I'm left with, put a CH3 over here and put the rest of the carbons. How many are we left with? That's 3. So I'm left with 2 carbons. So I'm going to put the other 2 carbons in this chain over here. So it's chiral. It's got a carboxylic acid. And you can check whether it has the formula C5H10O2 or not. So that's this one, okay? So we're done with this question. I'm going to move, Claire, if you have any questions, I'm going to move to the specimen paper question. So maybe I'm going to do this one. It's First question of 2022 specimen paper. Let me find 9701 specimen paper. Just 1 second. Sorry, 9701. So maybe this one, just 1 second. So now hopefully it's this one, just a second. Actually, this one, 2022, 02 hours. Okay. So it's this one, I think. State what is state what is meant by the term partition coefficient. So partition coefficients, it's the ratio of the solubility of a solute in two different immiscible liquids. Now the question is that ammonia is soluble in both water and organic solvents. An aqueous solution of ammonia is shaken with an immiscible organic solvent trichloromethane. The mixture is left to reach equilibrium. So what is happening is there are two solvents, water and an organic solvent, which they're calling it trichloromethane, which is Cl3 in this case. So let's assume that this is my beaker and it has aqueous ammonia. So ammonia is initially in water. So let's say this is water. So initially, just a second. So initially, you got water and it's aqueous ammonia. So there's ammonia that's mixed. I'm going to call ammonia X. So there's some X that is mixed in water, right? And it's shaken with an immiscible organic solvent trichloromethane. So it's mixed with CHCl3. Now what's going to happen is that some of the ammonia, which is X, is going to travel and it will eventually reach equilibrium, but some of it is going to mix in this organic solvent over here. So the mixture is left to reach equilibrium. The sample is taken from each layer and titrated with dilute hydrochloric acid. So there's some of ammonia over here, some ammonia here, and some ammonia in water, right? Now 25 cm³ sample from the trichloromethane layer. So first thing, he takes a sample, 25 cm³. And remember, it's got some ammonia mixed in it, right? So it's titrated with HCl. So can you figure out the moles of HCl? That's can anyone tell me what's this? 13 into 0.1 divided by 1000. Yeah, so what's 13 into 0.1 divided by 1000?
1.3 into 10 raised power minus 3.
That says you get 1.3. 1.3 into 10 power minus 3. What's the reaction between ammonia and HCl, right? It's going to form NH4Cl. So this is 1.3 times 10 power minus 3 moles. So the amount of ammonia is going to be exactly the same in the sample, 1.3 into 10 power minus 3 moles, because it's 1:1. Same thing. And it's a 25 cm³ sample, right? Now, okay, so the next part is he takes a sample of ammonia, and I'm also going to write this, that this is 10 cm³, right? This is 25 cm³ sample actually. So this one is a 25 cm³ sample that's taken. Then he takes some sample from the water layer as well, from the aqueous layer, 10 cm³ exactly. And he takes that ammonia, it's going to be the same reaction. He reacts it with HCl, it forms ammonium chloride. Okay, so it's going to form ammonium chloride. As in that case, what will happen is that, can anyone tell me what is this? how many moles is this?
1.25 into 10 raised power minus 3.
Sir?
ठीक है एक सेकंड माइक ऑफ कर दो अभी
Sir, can you please let my friend in, please? She's in the waiting room.
ठीक है I think I added that ठीक है अच्छा so this one we've got where were we? It's 1.25 into 10 power minus 3, right?
Yes.
So the ammonia is going to be the same moles, right? So basically what has happened is you're now able to figure out by titration, you know that 25 cm³ of this sample has these many moles of ammonia and the aqueous layer, 10 cm³ of the aqueous layer has this many moles of ammonia. You can find the concentration of ammonia in both layers. Because I think he's asking for KPC at the end. So for KPC, you would need the concentration of ammonia in both layers. So what's the concentration of ammonia in the first layer, the CHCl3 layer, and what's the concentration of ammonia in the second layer? That's going to be 1.25 times 10 power minus 3 moles divided by the volume in dm³. That's going to be 10 divided by 1000, right? And do the same thing over here for the other one, which is 1.3 times 10 power minus 3. And that's going to be divided by 25 cm³ in dm³. So what do we get for this? And you found the concentration. Let me make the whole expression. So what is KPC? KPC is between trichloromethane and water. So trichloromethane is going to be the numerator and water is going to be, so it's going to be the concentration of ammonia in the trichloromethane layer divided by the concentration of ammonia in the aqueous layer. And we know the concentration. So you find the concentration, and you divide the two things together. So you'll get your answer.
Sir, can you give a recap of organic, please?
ठीक है पहले मैं क्वेश्चन कर लूं उसके बाद कर लेते हैं.
All right.
So did anyone try and calculate this?
Sir, इसको जो आपने ऊपर वाली क्वेश्चन लिखी थी वो वाटर वाली है?
कौन सी ये वाली?
Yes, sir.
नहीं देखो what he's saying is that there are two solvents, right? There's CHCl3 and there's water, right? So what he did was okay, he put some aqueous ammonia. So ammonia initially was all in water. Okay, there was ammonia over here, and he added or he started shaking it with an immiscible organic solvent, which is trichloromethane. So what will happen? The ammonia over here will be in both layers. Now it's going to be some of it would be over here and some of it would be on this side as well. Your point clear? So, and then he separately titrated both layers. Okay, he took a sample of this layer. He took a 25 cm³ sample, titrated it with HCl. Okay, he gave you the moles of HCl. You were able to figure out the moles of ammonia. So in that 25 cm³ sample of the trichloromethane layer, you were able to figure out that you had these many moles of ammonia. So you had an idea of the concentration of ammonia in this layer. Then he took a separate sample, 10 cm³, but this time he took it from the aqueous layer. Okay, so when he took it from the aqueous layer, he titrated it with HCl, and he gave you the moles of HCl that were reacting with it. And you were able to figure out, okay, you got these many moles in 10 cm³. So you were able to figure out the concentration of ammonia in the aqueous layer as well as ammonia in the CHCl3 layer as well. So what is KPC? KPC is the concentration of the solute in one layer divided by the concentration of solute in the other layer. And the rule is that when they talk about KPC of ammonia between trichloromethane and water, the trichloromethane layer should be in the numerator and the water layer should be in the denominator. So, so but did anyone try to calculate this?
So how are we supposed to know which solvent needs to be in the numerator and which needs to be in the denominator?
Honey, that's what I said, that when it's written like this, that calculate the Kpc of ammonia between trichloromethane and water. So the first one that comes first, that's the one in the numerator, and the other one is in the denominator. No, it's not because remember,
0.416.
it's not always that water, because there might not be water. I mean, it's two immiscible liquids. It's not always that water is a liquid. As the next one, what's the next one? So yeah, so they gave me just 1 second. This question is not over yet. Next one is, as a butylamine is also soluble in both water and organic solvents, suggests how the numerical value of Kpc of butylamine between trichloromethane and water would be compared to the value of. So first thing, so what he's doing is he's switching ammonia. It's the same question, but he's switching ammonia with this thing. So what do you think? You got the same partition. One of them is water, the other one is trichloromethane, which is an organic solvent, which is less polar. One of them is polar. So which one is going to be more soluble in water, relatively speaking? We already know about ammonia, but butylamine, will it be more or will it be less soluble?
Most of them.
Less soluble.
It's going to be less soluble in water compared to ammonia. I'm going to explain. As it's going to be less soluble in water because this long carbon chain is hydrophobic, this thing. That doesn't form hydrogen bonds. The NH bonds, they do form hydrogen bonds, but this other part does not form hydrogen bonds. So there's a significant chunk of this molecule that is not going to interact with water. So it's not going to be as soluble as ammonia. Ammonia is a smaller molecule, and the whole molecule, every atom is attracted to water. Every atom is polar. N has lone pairs, H is very slight negative, H is partial positive. So this entire molecule is very soluble. This molecule has a big part that's not soluble in water. So this is going to be less soluble in water. If it's less soluble in water, that means there's going to be more ammonia there's going to be less ammonia in the water layer, relatively speaking. And there's going to be, because it's less soluble in water, and there's going to be more ammonia in the other layer. So the ratio, when you try to figure out the ratio, the concentration in the ammonia layer, in the aqueous layer, is going to be lesser for butylamine. And the concentration in the other organic layer, that's going to be more. So your Kpc value would increase when it comes to butylamine. So let me just recap this. What is happening is they're asking for a relative comparison. We did it for ammonia. If you replace the solvent with butylamine is going to be, compared to ammonia, it's going to be less soluble in water. And relatively speaking, that would mean that it's more soluble in the organic layer. So there's going to be less butylamine in the aqueous layer, more butylamine in the organic solvent layer. So if you divide the two values, it's going to give you a bigger number. That's why Kpc will increase. Is that clear?
So non-polar to non-polar.
Okay, you clear?
Yes.
Yes, sir.
Okay, so the next part, butylamide is much less basic than, so that's about,
So because alkylamines are more basic.
why? They are more basic, like in why?
So उनका donating effect होता है ना?
So you're going to talk about, it's a 1 mark question. So when it's a 1 mark question, you either explain why this is more basic or why this is less basic. You don't explain both because that's going to be redundant or you're just doing too much. So the reason is it's got an electron donating alkyl chain. So in electron donating alkyl chain, the negative charge density on the lone pair on N increases. So there's a stronger attraction for H plus 1. In the other case, what about the other one? When you have an amide, which is C double bond O, and So there's another CH3 as well, and NH2. So what happens in this case is that there's an electron withdrawing effect. The oxygen next door.
So this is the butanamide.
This is this one, butanamide. Okay.
Okay.
So there's an oxygen next door which is electronegative, so it has an electron withdrawing effect. The lone pair overlaps with benzene's pi electron cloud. Sorry, not the benzene pi electron cloud, the pi electron cloud in this Cdl bond O, because the oxygen has an electron withdrawing group. So the negative charge density over here decreases. So if there's an H+1 around, that H+1 will not be attracted to this lone pair. Okay. So remember, for bases, if you've got an electron donating, the more alkyl chains you have, the more basic it's going to be. The more electron withdrawing groups you have, the less basic it's going to be. So benzene is an electron withdrawing group. Amides, you got Cdl bond O, they have an electron withdrawing effect as well. So anything that has an electron withdrawing effect, the basicity will decrease. So I'm moving to the next question, which is
Sir, वो organic का please revision कराते हैं.
सर आप फरवरी मार्च 2022 के पेपर से सवाल करवा सकते हैं सर, तब मार्च 2022 वाला जो भी सबसे रीसेंट है.
अच्छा, वो मैं कराता हूँ, एक पहले मैं ये कर लूँ. एक क्वेश्चन 1 winter 1841. 1 second. एंड में पूरा पेपर कर लेंगे. Winter 18 QP41, that's question 1, right? So winter 1841, question on part D. 1 second. Question 1, there was somebody asking for organic chemistry. Question 1, part D. And D is.
Sir, वो organic का spiral chart reactions का मुश्किल का.
सर organic chemistry करा दें.
नहीं, वो तो मैं करा देता हूँ, ये क्वेश्चन मैं कर लूँगा.
उसके बहुत क्वेश्चंस हैं. ये सर आते हैं मुझे.
ये तुमने भेजा था?
नहीं, ये वो organic वाले में है.
अच्छा, नहीं, पहले कर लेते हैं ना कि this one is you've got to explain what is meant by the term partition coefficient. That's a basic definition. The partition coefficient of organic compound H between dichloromethane and water is 4.75. 2.5 grams of H was dissolved in water and made up to 100 cm cube. And you got, the whole question 1. So let me explain the whole question 1. 1 second. The first thing, gas liquid chromatography. It's very basic. All you have in gas liquid chromatography is, there's this, let's say there's a tube-like structure which is coiled, and this tube has a particular solvent that is present in it. It's lined with a solvent. That's your stationary phase. And there's this inert gas which is carrying your mixture, the vaporized mixture. That's so particles of any dye or whatever compound you're trying to separate, that's added, vaporized, and that's passed through at high pressures using an inert gas like helium through this tube. So if those particles are soluble in the stationary phase, which is the liquid over here, which is lining the tubes. So if it's soluble, the particles would take a longer time to travel through the tube because they would dissolve in the liquid, then they would vaporize again, then they would dissolve again. If the particles are not soluble or they don't mix with the liquid, the particles would continue to move forward and they would come out at the other end very, very quickly. So you'll have all sorts of particles. Some will not be attracted to the liquid in the stationary phase. So they would move out quickly. So X over here is something that is obtained in the first 5 minutes. So it's obtained very quickly. So X comes out first, right? So that indicates that X is not soluble or it's not dissolving in the liquid that is that the tube contains. Why on the other?
The liquid is alcohol. So can we talk about polar and non-polar?
उसके बाद वही question होगा ना. So the liquid is alcohol. So that means X is coming out very quickly. So the substance X over here that is passing through it is not really mixing with the liquid. So that means X is going to be non-polar, right? Because alcohol is very, very polar. And Z is taking a very long time to reach. It's taking almost 15 minutes to come out at the other end, right? So that means Z likes to dissolve in the alcohol. So it continuously dissolves in the alcohol. So that kind of indicates that Z is very polar, right? And Y is then something that's in between, right? Is that clear?
So you're saying the non-polar mixes with the very polar very well?
No,
So that is carbonic.
the first thing. Peter explained though. Remember, there's an alcohol that's lining. He did say that there's an alcohol, right? Did he say? Did he mention that there's an alcohol in this tube?
Yes, sir. It says the stationary phase is the liquid alcohol.
Achha, it says it over here. Okay. Achha, listen to this. You got an alcohol that's lining this tube, right? So if something that mixes with the alcohol, so it's going to take a longer time to come out at the other end. Is that point clear? Okay, it's like if the particle dissolves over here, it stays over there for a longer time, right? So it's going to take a much longer time to come out at the other end. If there's a particle, vaporized particle that doesn't mix with alcohol, so it just travels quickly and comes out very, very quickly. So the point is, okay, X takes a very small amount of time to reach the other end. So that means X is not dissolving in the alcohol. It just moves straight through the tube and comes out at the other end. So that means X would be a very non-polar substance because it's not mixing with the alcohol. Is that point clear?
Alcohol is polar, right?
Alcohol is polar, yes. Alcohol can form hydrogen bonds. And the other part is, okay, you got this mixture. There's Z. I mean, all X, Y, and Z actually enter through this opening over here. So Z is taking a very long time to pass through the tube. So that means Z continuously mixes with the alcohol and it stays behind. Then it vaporizes, then it travels a bit, then it mixes with the alcohol again. So Z is continuously mixing with the alcohol. So Z must be very, very polar that it forms hydrogen bonds and mixes with the alcohol. So it takes a longer time for it to come out at the other end. Is that point clear?
Yes, sir.
Achha, so you just have to figure out, there were 3 compounds that were added. An aldehyde, an alkane, and a carboxylic acid. So X must be the alkane. Z must be the very polar carboxylic acid because it's capable of forming hydrogen bonds. And Y over here must be the aldehyde, which is something that's an in-between. That's polar, but not that polar. It's got permanent dipoles only. Can you guys hear me?
Yes, sir.
Yes, sir.
ठीक है शामी ने चेक कर लो अपना प्लेट के करीब बैठ जाओ ठीक है अच्छा so this part clear? So this is what the explanation is going to be as well. So that's the first part, and that's pretty much all there is to gas chromatography. That's how it would have been the other way around if you had a non-polar solvent. If you had a non-polar solvent, remember this rule that polar things, they mix with polar substances. And vice versa, non-polar substances mixed with non-polar. So it would have been the other way around if there was a non-polar liquid in this one. If there was a non-polar liquid, the alkane would have taken the longest time because the alkane would dissolve in the non-polar, so it would just stay behind. It would take a long time for it to reach the other end. And in a non-polar liquid, the carboxylic acid will not mix. So the carboxylic acid would travel as a vapor with the inert gas and travel quickly outside of the tube and reach the other end. So that's X, Y, and Z. We can move to the other part, which is a student calculates the areas underneath the 3 peaks in the chromatogram. The other thing information that you get from a chromatogram is gas chromatogram is you figure out the quantity of the liquid of each substance in the mixture. I mean, you know that there's this much X, there's this much Y, and there's this much Z. So clearly there's a lot more Z that's being obtained. and a lot less X that's being obtained. So the area of the peaks or the absorption of the peaks kind of indicates how much of the substance is mixed. As a mass spectroscopy is in AS, but remember a lot of things in AS are basics for A2. Most A2 questions, specifically for NMR, they are built on mass spectroscopy. So that's why it's a basic thing that you should know, because the question will depend on mass spectroscopy. As I'm moving on, this one, calculate the percentage of mass in the original mixture of the compound responsible for peak Z. So you got this much Z, and that's the total area. So it's just going to be 47. That's the absorption that you obtained for Z, divided by the total, which is 19 plus 32 plus 47, and into 100, you will get the percentage. Now, the other part is the mass spectrum of halogenoalkane containing one chlorine atom or bromine atom will show an additional peak at M+2. State the isotopes of chlorine and bromine responsible for the M+2 peak. So chlorine
and 37.
Okay, so you got 37 and bromine is
81.
81. Okay. And in both cases, if you have a 37, what's the ratio of the MM+2? That's going to be 3:1.
3:1.
And this case, if you've got
1:1.
Okay, that's going to be 1:1. Because you can either have bromine 79 or you can have bromine 81, and they both have equal probability. So, as the next one is the mass spectrum of bromo. Actually, now the only thing about this one, about your A2 paper now is probably you wouldn't get such a direct question. I mean, this one is totally targeting mass spectroscopy. So your question would be on something else, but there would be some mass spectroscopy knowledge that would be required. So you wouldn't get these kind of questions probably. But somewhere in between, there would be knowledge about mass spectroscopy would be required. As the mass spectrum of bromochloromethane has a molecular ion peak M at an ME value of 128. It also has an M+2, M+4, suggests the identity of the molecular ion that gives rise to these peaks. So bromine could either be 79 or it could be 81. So the mass would change by 2. The Cl could either be 35 or it could be 37. So the M peak is because of the smallest isotopes. So in that case, it's going to be CH2. The Br would be the 79 one, and the Cl would be the one that has a mass of 35. So in that case, you'll get the peak at 128. The peak will have a mass, an increase in mass by 2 when either one of them is the heavier isotope. So it's going to be bromine 81, or it could be Cl with Cl35, or you could have the bromine can be 79 and the Cl could be the heavier one. And M+4 is obtained when both of them are the heavier one. So you could have bromine 81 and Cl is 37. Make sure to put a positive charge sign on top of whatever molecular ion or fragment that you're writing. Okay. As any other question, we can continue with the specimen paper.
So can we do delta H of hydration and solution के questions?
ये एनर्जी साइकिल वाला करा दें.
सर इस क्वेश्चन का डी पार्ट डी का सेकंड पार्ट करना है.
मेरे ख्याल से आज से
अच्छा एक D का, just 1 second. This one?
Yes, sir.
So this one, the partition coefficient, again, partition coefficient. So it's a compound H between dichloromethane and water. Okay, that's the 2. And dichloromethane would be the numerator and water would be the denominator. So the value is already given, that's 4.75. Now 2.5 grams of compound H was dissolved, right, in 100 cm cube and made up to 100 cm cube in a volumetric flask. And 50, so the first thing, you got a 250, sorry, 2.5 grams. So you got a 2.5 gram substance mixed, whatever H is, and that's mixed in 100 cm cube, right? So you got a 100 cm cube water, and this is then 50 cm cube of this solution was shaken with. So you put 50 cm cube into some other apparatus, just 50 cm cube. So 50
half हो
cm cube.
जाएगी उसकी.
That makes sense. It's just going to be 1 point. So that means you got 1.25 grams, right? That's a quicker way of doing this, because you added 2.5 grams in 100 cm cube. So if you take a 50 cm cube sample out, so that will have 1.25 grams of it. That makes things easier, and you're shaking it with 10 cm cube of dichloromethane.
Oh,
So
sorry,
there
now I
is-
get it. That was the only confusion.
X over X divided by 10 over
Any X from the
1.25
next
minus X.
So some of it will move to the dichloromethane layer, so that's going to be X. So over here, it's going to be 1.25 minus X. So some of it would travel into the other layer. And you already know what the KPC value is, which is 4.75. So all you have to do is equal to, denominator would be X over 10. X grams in 10 cm cube and 1.25 minus X grams in 50 cm cube. And you will equate this as to 4.75. That's your KPC expression.
So yeah.
And you'll solve this.
So वो वाले questions करवा दें जिसके ना energy cycle बनाने को वो कहते हैं, but they've given the lattice energy when they're asking to find. They're asking to find something else, either bond energy or something like delta H of solution or action.
वो देखना पड़ेगा, just 1 second. It's do you have questions on that? Okay, I have questions on Bond-Neighbor cycle specifically.
So specifically वाले bond-neighbor cycle वाले हो जाते हैं, but the other cycles are confusing. जैसे आज एक
Bond-Neighbor का भी एक
group पे भी
example
भेजा
वैसे
था,
करा दें।
एक group पे भी भेजा था आज question May June 19 का I think.
हाँ, मुझे क्वेश्चन बता दो क्योंकि वो थोड़े रेयर है, मुझे पता लग गया कौन सा क्वेश्चन आप बात कर रहे हैं, बट देयर
Okay सर, एक सेकंड में देखती हूँ.
इसमें भी शायद हो, एक सेकंड, 1 second.
Sorry?
Yes.
Do we still have to know about cisplatin and
You don't have to know that in too much detail. You just need to know that it's just one line, like that would be sufficient, because I mean it's still there, the cis and transplatin. That's the only thing you should know is that it's an anti-cancer drug, and I mean the basis DNA part is all gone, so no one is going to ask you about that.
Okay,
So
thank
एक
you.
question है 21 के अंदर है October November 42.
Summer 21. अच्छा,
नहीं October November.
Question paper 42.
Yeah. I think question 3 था, ये नहीं question 1 ही था उसका.
ठीक है, just 1 second. Is it this one?
Yes.
Actually, sulfur exists as acid molecule in the solid state. You're talking about this one, right? Use the data and calculate the enthalpy change for the reaction of S8 to 8S, right? So, so what you do first thing? This is all about. It's the same AS Hess cycle, okay? Okay, all you have to figure out S8 solid, right?
Yes.
And it's turning into 8S gas. So that's you just need to figure out another route. Okay, and this is not going to be easy. First thing, I don't think radium has anything to do with this. There's this equation which I can link. I'm just going to randomly link any equation that can be connected with this. So I've got S8, but then there is 2 electrons as well, and it's forming S2 minus 1. So, and I would have to multiply it by 8, right? So I got to multiply it by 8. So first thing, the two electrons as well. So I need to add how many electrons? If I multiply it by 8, that's going to be 16 electrons added to it, right?
Yeah.
So I'm going to add 16 electrons on both sides. That will not change this path. I mean, this path, the 16 electrons are not doing anything. So this path still remains the same. That's not changing. But I just need to connect this. S8 bond, you got 16 electrons added to it, and it will form how many sulfurs? It will form 8 sulfur 2 minus gaseous ions. And this would be plus 555, and that's going to be multiplied by
8.
8. Just make sure we didn't do anything wrong. So it's S8 plus 16 electrons plus 8 sulfur 2 minus, right? So S8 plus 16 electrons forms 8 sulfur 2 minus gaseous. So that's this path. Now I need to link this up with this one. So I've got sulfur gaseous, and it's getting 16 electrons. So sulfur, I've been given the electron of. I've been given this electron affinity of this. So first electron affinity and the second electron affinity of sulfur. So
Sum of that into 8 again.
And dono electron affinities, that's minus 200 plus 532, right?
So that's multiplied by 8.
532, and I'm doing this for 8 sulfurs. Okay, so cycle to complete. Did I miss anything? Yep, I think that's it. So we figured out the path. So that's my path. So I just need to change the sign of this thing. Is that clear?
Yes.
But it's like the questions mushkil honge, lekin it's not impossible. It's like most of them are Born-Haber cycles, but just try and put that equation in the middle and try to connect as many equations as possible you can with this one. So the cycle would, I mean, most of the time cycle will be formed.
Sir, एक delta H of solution वाला भी करवा दें.
Sir, organic करा दें sir अब reactions.
रुक जाओ एक सेकंड. नहीं solution वाला मुझे question दोगे फिर होगा, ठीक है?
Sir, I think आपके topicals के अंदर था आपने जो भेजे हुए हैं.
So just a second. बस ये 10 मिनट देना फिर organic शुरू कर देंगे. Just 1 second. We've got
okay, sir.
Let me just answer this question. February, March 22. I haven't actually seen February, March 22. I don't know where it is. 9701. M22 42, sorry.
Sir, I have the paper. Should I send it on WhatsApp?
You can try and send this on WhatsApp, but it's probably not on the. I think that's W19. So it's probably not on the. Send it on WhatsApp.
Okay, 1 second.
But yeah, let's try and solve this whole paper. उसमें organic पहले कर लेंगे.
Sir, energy cycle जब बनाते हैं, if we have the atomization energy, तो हम जब उसको multiply करते हैं with the balance equation, उसके बाद we don't write that again in the other steps, right?
No, I didn't get it. Atomization in the Born-Haber cycle.
Yeah.
Let me try and do one question.
Okay.
So I've got the paper. 1 second. So this is February, March, right? So which question in this one? It's firstly. Question 2, part B2. Question 2. So he's saying that use this information and your answer to calculate the temperature in calories at which the reaction C becomes feasible. Sure, working if you're unable to do B1, so it's related to B1. So you have to figure out the entropy change for reaction number 1. So that is simple. All you have to do is
Products minus reactants.
okay, so it's the products minus the reactant. So it's Si8Cl3, that's 314 plus H2, that's 131. Both of them are 1 mole, TK, and minus, that's product minus reactants. So Si is 19 and HCl is 187 times 3. TK, does it even know what this is?
Minus 135. Somebody confirm.
TK minus 135. So this one is minus 135. So now the next part is you've got reaction 3 is the reverse of reaction 2 and is used to obtain pure silicon. So let me just compare this. So if it's the reverse, what will happen to the entropy change, by the way?
Plus ho jayegi.
Yeah, the sign will change because the product will now be the reactant and the reactor will now be the product. So if you do product minus reactants, it's going to be the exact opposite. So it will be plus 135. So this one is delta S is plus 135 for this one.
So why can't we change the sign of delta H?
You can change the sign if you reverse it. You can change the sign. That's going to be exactly the opposite. Okay.
So yeah.
But they didn't give the sign of delta H. They gave the delta H sign for this one. Okay, so you don't need to change that. They've already given you the right value.
Okay.
Achha, so use this information to calculate the temperature in kelvins at which the reaction 3. So when does the reaction become feasible? The delta G has to be
Less than 0.
So delta G is equal to delta H minus
T delta S.
and that should be less than 0. And if that is less than 0, delta H is given, that's 219.3 minus T you're looking for, and the delta S is given, that's 135 divided by 1000.
Yeah.
Okay, because that's in joules and this is in kilojoules. So you have to make the unit the same. So you'll just solve this and you'll figure out the temperature. Okay? And make sure when you have an inequality, if you change the sign, if you make something negative to positive, the inequality direction will change as well. Because that's about it. I think that was fairly straightforward. So we're starting with organic now. Okay, we're going to try and do. Part C, just 1 second. Silicon can also be produced by electrolysis of SiO2 dissolved in molten CaCl2. The relevant half equation for the cathode is shown. Calculate the time in seconds required to produce 1 gram of silicon using a current of, as you know, the substances are produced at the cathode. So you're looking for the time, 1 gram of silicon. First thing, how many moles do you have? That's 1 divided by the AR of silicon, which I think is 28, right? So, okay, what's 1 divided by 28?
0.0357.
So we're getting 0.0357 moles. Using those, we can figure out the moles of electrons. The moles of electrons are going to be 1:4. It's going to be 4 times more. So the moles of electrons would be
0.143.
0.143 moles. Okay. Multiplied by 4. Okay. It's this multiplied by 4, you get the moles of electrons. So once you have the moles of electrons, you can figure out the charge by using the Faraday constant, because 1 mole of electrons has a charge of 96,500 coulombs. So if you have 0.143 moles of electrons, then what is the charge?
13,785.
Is that 13,000?
785.
So we're getting 785 coulombs, right? And once you have the total charge that's passing, you can use Q is equal to IT to figure out the time, which is 13,785 coulombs, and you know the current as well, that's 6 amperes, and you can figure out what the time is in seconds. Okay. Now, the only thing, remember this, these questions, you just need two things. You need Q is equal to IT, and you need 1 mole of electrons has 96,500 coulombs charge. Now, there are two ways of solving this. Now, in this case, we immediately knew that you can't do Q is equal to IT because you don't know what T is, right? So you would have to go all the way around to figure out the moles of electrons. You'll figure out the charge. When you figure out charge, you can figure out time.
Sir, आपने एक नया फॉर्मूला भी बताया था ग्रुप पे, वो कब यूज करेंगे?
Actually, that new one is it's just a formula. Okay? There's nothing to it. It's about delta G, which is okay. I can't. It's my what is it? It's minus n delta S, and exactly it's the E naught cell if it's a feasible reaction into the Faraday constant. Sorry. Okay, that was what the formula was. I said this one is. I haven't seen any questions. Somebody sent me a question, but I haven't seen any questions so far on this. This is new. All the rest to this, there's no. I mean, you don't have to go into a lot of detail with this. All you have to do is when you calculate an E naught cell of a particular reaction, using that E naught cell, you can figure out the Gibbs free energy as well. There's another formula of finding Gibbs free energy using E naught cell. So if you have an E naught cell, you just have to multiply it by the Faraday constant, and n is the number of electrons that are being gained or
Transferred
lost
in the reaction.
Okay, that's it. So there's this formula in which if you have the E naught cell, you can convert that into Gibbs free energy. That's it. Or vice versa, if you have Gibbs free energy. So that's it. Okay. Makes sense. 3C1. It must be from this. I mean, this is the only paper that has this formula, which is
ये वाला है ऊपर.
C1, right? Because they were asking you to, they gave you the Gibbs free energy, and you were supposed to figure out. You can figure out the E naught cell using that. You had the two reactions. You didn't have the. We can try and do this one. So the standard reduction potentials are given. E naughts are given. For this one is given. For the other one, it's not given. So you can figure out the E naught cell using this, and the E naught cell would be delta G.
Number of electrons हम E naught जिसकी दी हुई है उसकी डालेंगे, like 4 electrons.
When you balance it, I said that's the overall equation, right? So this is the overall equation. I said that's the overall equation. So the overall equation is given. First thing is you can. So how many electrons are being lost or gained? So there's this equation. There's one O2 involved, right? So if there's one O2, so that means 4 electrons are being gained by that one O2, right? Is that clear?
Yeah.
जी.
So N over here is 4.
सही है.
And so N over here is 4, that's minus 4. E naught cell, you can figure that out. Faraday constant is 96,500.
And Gibbs free minus 460, 436.
That's given. So you can figure out the E naught cell. Once you have the E naught cell, all you have to do is E naught cell is what? E naught cell is higher potential or reduction potential minus oxidation potential. As a first thing, can you tell me what the E naught cell is coming out to be? Okay, the delta G is minus 436.1.
1.13 into 10 to the minus 3.
So that's 1.13 into 10 to the minus 3. Now, what is the reduction E naught? O2 is the one that's the reactant. So this is the reduction equation, right? The other one is going to be the oxidation equation where the TL3 plus is turning into, it's going in the backward direction, right? That's the oxidation equation. You can even confirm that TL3 plus is turning into TiO2 plus. So the reduction E naught is 1.23. So the other one is the oxidation E naught, and we don't know what that is. So that's going to be taken as X. So you'll be able to figure out what the E naught of this thing is once you find X. This value is coming out to be slightly smaller, so you can double check with the marking scheme whether this is correct or not. Yes. 1.13. I'll just double check with the marking scheme.
इसका part को दिखा दो.
नहीं, कौन सा part? One second. Can anyone check why are we? Is this correct or not?
So 1.2 तो नहीं है. 1.2 into 10
The
to the
answer
minus
is
3.
the answer is 1.13.
अच्छा.
Without the, let me just quickly check the units. Do we take delta G in joules or kilojoules?
Kilojoules.
Oh,
Yeah, but we can just confirm whether.
oh,
I mean, that's
1.1. Sorry,
नहीं,
1.2
this-
आ रहा है.
the 436.1 is supposed to be divided by 1000.
Sorry, 1.2 आ रहा है. Not sir.
Supposed to
नहीं,
be-
वो यही आ रहा है. That's fine. उसके अंदर issue नहीं है. The delta G is going to be taken in joules. That is what the
Yeah.
market scheme is saying.
Yeah.
Okay, the delta G has to be taken in joules.
तो
So
उसको
the
हम multiply by 1000 करें. Divide by 1000 करें.
multiplied by 1000.
Mm.
Okay, that will give you 1.13. Okay, so I mean that's the only question we have to go with. So that's the units that they're using. And I'll just confirm.
0.1 है. Answer.
हाँ, ठीक है. Nidhi, I'll confirm, but I'm pretty sure that's going to be taken in joules. Okay, I'll confirm later in the group as well. But just make sure, okay, right now, according to the market scheme, this is going to be taken in joules. Okay, and I'll check and get back to you on this.
Sir,
Yes.
I wanted to ask a general person के sir यहाँ पे standard electrode potential जैसे 1.23 दिया in forward direction. Sir अगर हम backward direction में रहेंगे तो line change होगा या 1.23 रहेगा plus?
नहीं, पहली बात है कि it's not changing because of the direction. You're calculating a difference. How do you calculate potential difference? It's a higher potential minus lower potential, right? So the minus sign is not because you're changing the direction. The potential is the same. This is 1.23 volts, whether you're going forward or whether you're going backward. ठीक है, वो जो minus sign है ना, that's because of the difference. You're calculating a difference. Do you get the point? It's like, how do you calculate potential difference? It's higher potential minus the lower potential. So it's the difference. So the reason the higher potential is taken as 1.23. Even if it was backward, the potential would still be 1.23. But when you calculate the difference, it's going to be higher potential minus lower potential. So that's where when you calculate the difference, that's where you get the minus sign. Okay. तो उसको उससे separate करो. The potential is not changing. The potential is the same. You just trying to calculate a difference. Is that clear?
Yes. Yes. Thank you.
सर अगर ये हो गया तो एक एनर्जी साइकिल वाला करवा दें फिर ऑर्गेनिक शुरू करवा
नहीं,
दें
और ठीक है, और कोई क्वेश्चन है? मतलब वो क्वेश्चन मुझे बताओ कोई।
सर ये मैं सवाल पूछूं?
हाँ हाँ
सर ये समर 19 पेपर 4-2 है।
समर 4-2 PDF on sec. अच्छा, which question?
सर क्वेश्चन 5 सी पार्ट
5. अच्छा, question 5 C part. ठीक है, this is the same energy cycle question. Just very quickly, we got. He's saying determine the standard enthalpy change of solution of potassium. Enthalpy change of solution of potassium K3PO4 solid, right? So what is solution? K3PO4 solid. It dissolves in water, aqueous state, turns into aqueous. So now one thing is, make sure whenever you have aqueous, dissociate the ionic compound. There's going to be 3 K+1 aqueous ions. And there's going to be pure. There's going to be PO4 minus 3 aqueous ions. As I remember, there's a lot of confusion caused by this. Sometimes they write it as K3PO4 aqueous. Sometimes the question, to solve the question, you would have to dissociate it. Both of these, they mean the same thing. They're exactly the same thing. So if you're not able to solve it using K3PO4 aqueous, think of it as separate aqueous ions. So anyways, that's the one that you're looking for. So you're going to create another path. So you're given the enthalpy of formation of K3PO4 solid. So I've got K3PO4 solid over here. What is enthalpy of formation? That the compound is formed from its constituent elements. What are the elements? There are 3 potassiums, solid.
Potassium and
phosphorus, which is solid, and you got 2 oxygen gas molecule, which is gas. Plus you have aqueous, which is not doing anything in this part over here. So this is minus 2035. That's minus 2035, and the next part is you've got potassium solid going to K+1, and you've got phosphorus plus 2O2 plus 3 electrons. So that can be done in, I think, one part, which is this one. If you look carefully, 3 potassiums, I'm going to multiply this by 3. So you can see over here that 3 potassiums are turning into 3 potassium ions. So that's minus 251 times 3. And they're losing 3 electrons, right? And who's gaining those 3 electrons? The phosphorus with 2 oxygens. So you got a phosphorus with 2 oxygens. They're gaining those 3 electrons to form PO4 minus 3. So that's minus 1284. So I've connected these two in the same path. So that's my cycle that's complete now. Is that clear? So that is what my path is. Okay. So और कोई question था? So we can start with organic questions now. Okay, we'll just do organic questions. In exothermic, so in exothermic you have remember in energy. I said one thing about this one. When you have in exothermic or endothermic reaction, enthalpy change, the plus and the minus sign, they don't indicate the size of the value. They indicate the direction. It's not like if something is plus 100 joules and the other one is minus 100 joules. That does not mean or indicate that one of them is a bigger value, the other one is a smaller value. They're both the same energy. It's only the direction that's important. That plus and minus, they represent direction. So when you're comparing enthalpy change values, you compare the value. Okay, the direction will just tell you whether it's exothermic or whether it's endothermic. So if you've got two values, like you've got minus 500 kilojoules and there is another value which is minus 100 kilojoules. And if they ask you which one is more exothermic, then although minus 500 is on the number line, it's a smaller value, but don't think of the minus and plus sign as it's the direction. It's not used as a sign. It's used as a direction. So ignore the minus 500 is the bigger value, 100 is the smaller value. That is more exothermic, this is less exothermic. Okay, hopefully that clears the point. Right, so don't get confused with this. Don't think that minus 100 is bigger than minus 500, it's not. Take the values separately and the direction separately. Think of the direction separately. So okay, let's start, and let me just close a few tabs. So we can start. We can start with the specimen paper organic part, right? So I'm going to start with this one. This one is again a typical. It's a typical organic question. The reaction also forms an isomer 4-nitro methyl benzene is a byproduct. Draw the structure of this byproduct. So also forms an isomer, which is 4-nitromethyl as a byproduct. So an isomer of 4-nitro. So you've got, what type of group is CH3? Is it 2,4,6 or is it 3,5?
Electron donating.
2,4.
Okay, so it's a 2,4. Okay, so it's a 2,4 directing group. So the NO2 is either going to be on the 4th position or the other one, what's the other isomer? That's going to be on the 2nd position. So that's your, so it's an electron donating group, and that's your other byproduct. Write an equation for the reaction of H2O3 and H2SO4. This is a very important reaction because I said, describe how the structure and bonding of the 6-membered ring in intermediate T differ from those in the methyl benzene. In your answer, refer to the hybridization, the pi bonding, and the bond angles in the ring system. So basically, you have to talk about pi bonding and the bond angles in the ring system. And he's not talking about benzene over here. He's talking about the intermediate T, which is this one. So first thing, how is it different? When carbon over here, this carbon over here is making 4 bonds. So what type of hybridization is this?
sp3.
Because that's sp3. And when it is sp3, what is the shape and bond angles?
Tetrahedral.
Okay, so it's tetrahedral. It's making 4 bonds, and the bond angles are 109.5 degrees. And it's making 4 sigma bonds, right? Now, what about, so it's making 4 sigma bonds. What about these other ones? These are your proper benzene carbons, right?
sp2 hybridized.
So all of these are sp2 hybridized, which means that they're making 3 bonds, and they've got a 4th electron in the p orbital, which is making pi bonds. So you're going to talk about the hybridization, and all the other 5 carbon atoms are sp2 hybridized, and their shape is trigonal planar, and the angle would be 120 degrees, and they would be making 3 sigma bonds, and they will be making one pi bond. Okay, so you just have to write this in words. If you had a benzene, then all 6 would have been exactly the same. But right now there's one of them which is making 4 bonds. So now the next part is you've got this reaction mechanism. Give the systematic name of W. So carboxylic acid has the highest precedence. So this is benzoic acid. Do you remember carboxylic acids have the highest precedence, and amine changes into amino, and that's 4-amino benzoic acid. As I suggest, remember this, although you're not going to get a very complicated question on this, but remember the precedence of AS, that you had carboxylic acids followed by aldehydes and ketones. They had higher precedences. Then you had alcohols, and then you had amines. Now suggest the reagents and conditions for step number 1. How do you convert NO2 to NH2? एक सेकंड, क्या कह रहे हो?
10 और HCl इस्तेमाल करते हैं under reflux.
हाँ ठीक है, वो सारे रिवाइज भी कर लेते हैं. Let me just open the chart as well. Just 1 second. 10 plus concentrated HCl. ठीक है, remember
Concentrated. Or can we use NaOH as well?
नहीं.
Okay.
I've never seen that in the anywhere. ठीक है. Let's say just 1 second. कहाँ पे ये? अच्छा, this one. चले. Starting with the first one, this was this part, 10 plus concentrated HCl, right? And then you had the NH2 was turning into an amide. How do you make an amide? Like this is NH2. So you need, remember, so that's a, the amide are always made with acyl chlorides.
तो COCl क्या होता है?
वही acyl chloride है, CH3 COCl. आवाज हमारी कम आ रही है ऐसे. ठीक है, so these two will join up and the H and the Cl will get knocked out, right? So remember, amides are always made with acyl chlorides. Now, the next part is that the amide still remains. How do you convert a methyl benzene into a carboxylic group? And
Oxidation.
ठीक है, that's oxidation. ठीक है, that's KMNO4. So that's KMNO4 acidified and reflux, right? So over here, carboxylic acid remains the same. The amide is broken back into NH2. So how do you hydrolyze the amide?
Sir, reduction, LiAl.
No, not reduction. No, you're breaking it. ठीक है? एक है कि you convert it. One of them is you got an amide and you break the amide. So you reduce it with LiLH4. In that case, the serial bond only changes into CH2. That's it. But over here, it's breaking down. You break it down by dilute acid or dilute alkali, and the double bond O, it's going to break in the middle. ठीक है? It's going to form carboxylic acid. And this other part would be your amine part. So it's the reverse. What is happening here is this part, the serial bond O part, is breaking off. So that would be dilute acid.
So hydrolysis.
And it is hydrolysis, it's reflux.
So you can use either dilute acid or dilute alkali, right?
You can use dilute alkali as well. As I said, next part, the reason I wouldn't use dilute alkali over here is they gave me a carboxylic acid in the product. When you use a dilute alkali, you don't get a carboxylic acid, you get a salt of the carboxylic acid. But a CO -1, and because the alkali will react with it, right? So because they... That's the last one is esterification. That's and what do you need for esterification? You need concentrated H2SO4 and reflux. The next I mean, it's all about conditions. Okay. A sample of benzocaine was analyzed by carbon-13 NMR and proton NMR. Predict the number of peaks in the carbon-13 of benzocaine. What's benzocaine? Can't get benzocaine. Benzocaine is used. This is benzocaine. So how many carbon-13 environments does this have? Starting with, there's this bottom carbon, that's environment number 1. Then you've got these 2 carbons in the same environment. That's they would resonate at the same frequency. So it's 3. This is the 4th one. This is 5th and 6th and 7th, right? So 7 peaks. You got 7 peaks for that. And now you have the proton NMR. So the proton NMR looks like this. Pretty easy. Okay, this one is a triplet peak. So who's the neighborhood?
CH2.
So this must be the CH3 peak, because the neighbor is CH2. So it must be this one, because that's the one that's going to be triplet, right? I said then you've got a quadruplet peak. So who's the neighbor?
CH3 तो ये CH2
CH2 वाला होगा ये.
हाँ ठीक है, the neighbor is CH3, right? So this must be the CH2 one. That's going to be a quadruplet peak, because right next door there is a CH3. I said then you have a singlet. Who's going to give me a singlet?
NH2.
Remember NH2 and OH are always singlets. Okay? They're always singlets, and they don't cause any splitting as well. Okay? So these 2 are always singlets.
तो OH को क्यों नहीं कंसीडर किया? या किसी को भी कंसीडर कर सकते हैं?
नहीं, OH तो है ही नहीं. They've already told me that this thing belongs to this molecule over here.
CO को हमने कंसीडर क्यों नहीं किया?
किसको? इसको? Where are the? There is no hydrogen here. This is HNMR.
Okay.
So you're looking for hydrogens to resonate. You have CH3. These hydrogens are resonating. These hydrogens are resonating. You got 2 hydrogens over here. They're resonating, and there are 4 hydrogens on the benzene, right? So right now we're not focusing on the carbon environment. We're focusing on the hydrogens. Is that clear?
Yes, sir.
Achha, so remember, this was easy. You just have to match because this was easy.
Multiplet किसका होगा?
Last year, again, that's the benzene one. And remember, benzene is usually a multiplet because not all hydrogens have exactly the same environment.
Benzene पूरा का पूरा?
Because 4 hydrogens, there are 4 hydrogens, one over here, one on this side, one on this side, right? So all 4 hydrogens don't have exactly the same environment. So it's always something that looks like this.
Okay.
Isha, it's better to learn them anyways, like even, whether it's given or not.
Catch you, sir.
2, 4, 3, 5 directing groups. So is this part clear? So all you have to do is you have to figure out the environment of the proton. You don't even need the data booklet in this case. You don't need to open it, because by just looking at the splitting pattern, you were able to figure out this one, and this one. So the 4th one was automatically this one. So the number of hydrogen atoms responsible for the peak. So you were able to tell that these 4 hydrogens are resonating over here. 2 hydrogens, they're a singlet peak. 2 hydrogens, that's a quadruplet peak. 3 hydrogens over here, that's a triplet peak. So you were able to figure out everything without opening a data booklet. Just explain the splitting pattern for the absorption at 1.2. So they're asking for the splitting pattern. So just tell them that the neighborhood is CH2, that's it. And they give you a table for that as well, right next to it. Anyways, another organic question. This one is about not really sure what it's about. It's benzocaine can also
as a compound बना रहे हैं.
ठीक है. Can also be used to synthesize the azo compound S. So what is the first step when you want to make an azo compound? What does the NH2 need to turn into?
Disonium ion.
Okay, so the NH2 needs to turn into a disonium ion. That's NaNO2 plus HCl, and the temperature's got to be less than
HNO2 plus HCl.
ठीक है, ये वो कर लो.
ये
So
नाइट्राइल का सिस्टम है या नहीं?
कौन सा?
ये नाइट्राइल और डायज़ोनियम अलग-अलग चीजें हैं, एक ही चीज है?
अलग है ना. Nitrile is CN.
Oh.
Disonium ion is in triple bond N plus 1. Achha, so this thing at the bottom will turn into a disonium ion. It's N triple bond N plus 1, and you will have COO and CH2 and.
अच्छा ठीक है, वो कैसे है?
Achha, then you need an activated benzene. So this disonium ion will act as an electrophile. It will get attracted to the electron cloud over here, and it will bond with it. So what will happen is that the two benzene rings will get connected. The N triple bond N plus 1 will get attracted to the phenol benzene. Or you got COO and CH2 CH3 on the other side.
सर लेकिन साथ में NOH डाला है aqueous, तो फिर OH जो phenol होगा उसमें से ONA बनेगा ना?
हाँ, लेकिन the thing is that the phenol is reformed at the end. The reason is an H gets substituted over here at the end. So that H plus 1 when it leaves, this H plus 1 when it leaves, it neutralizes the NOH.
That happens with carboxylic acid, right? Na C double अगर NaOH हो तो it further becomes a salt C double bond O minus and
it can happen over here as well. Okay, I mean it can happen over here. It's a phenol, right? But the thing is that there's an H. The NaOH gets neutralized because there's an H plus 1. Like, do you know what the mechanism is for electrophilic substitution? One second.
Yeah.
Yes, sir.
Okay, part 1. 1 second. Whenever you have electrophilic substitution, an H plus 1 leaves the benzene ring, right? So whenever you have, so whenever you have any type of electrophilic substitution, the H plus 1 leaves at the end. So it is this H plus 1 that is neutralizing the NaOH or reacting with the NaOH. The NaOH is added because it speeds up the reaction. It makes it easier for the H plus 1 to leave the benzene. Okay, the H plus 1 has to be accepted by someone, right? So the OH ions from NaOH will accept it. So that is why you add the NaOH. Although this is not important, just remember that there's an H plus 1 that's going to be leaving this carbon over here at this point over here. So who's going to accept it? That's going to get accepted by the alkali over here. Is this clear?
Yes, sir.
So the NaOH purpose is not to react with the phenol in this case. It's actually getting neutralized by the H plus 1 that's leaving here. So which is why you don't need to worry about it. It's going to be, most likely it's going to be a phenol that will be formed at the end. Although phenols do react with NaOH. Is that clear?
Yes, sir.
I just suggest the reagents and use for step 1, that's NaNO2 plus HCl or HNO2 temperature less than 10. Suggest structures of compound, we did that.
Okay.
So this is about, that's the only question. I think the organic questions over here are finished. So I'll just open another paper. Okay. So let's do, this is a very frequently asked question, which is about the structure of benzene. And by reference to the formation of sigma and pi bonds, describe and explain the shape of a benzene molecule C6.
6 sigma bonds.
Okay, so you're gonna talk about you can talk about everything about benzene. That is that the carbon is
sp2 hybridized.
Okay, sp2 hybridized. It's trigonal planar, and each carbon atom is make
इसमें trigonal planar mention करेंगे या hexagonal planar इनका जो shape
Trigonal planar is carbon ka, and overall is hexagonal
overall it's
planar.
Okay. And you're going to mention that each there are 6 p orbitals that will overlap. Okay, just explain the whole thing that each carbon is making. Tell them about the hybridization of carbon.
बताने कि carbon के दरमियान sp2 है.
हाँ, वो बता दो क्योंकि it's because remember when you have they give you so many lines. Now it's a very vague open-ended question, so it's better to actually explain as much as possible. Okay, there's a pp overlap that's happening, and between the carbon and hydrogen, and between the carbon there's यहाँ पे it's the sp2 of the carbon atom overlapping with the hydrogen. That's an s orbital of the hydrogen atom, right? Between the carbon and carbon, it's an sp2 overlapping with an sp2, and the pi bonding is happening because you've got a p orbital overlapping with the p orbital of the neighboring carbon atom. And tell them that each carbon atom is sp2, it's trigonal planar, and overall the shape of the molecule will be hexagonal planar. As the next part, you've got write an equation to show how the H2SO4 generates the electrophile. So again, it's the same equation that you have to write between the two. Draw the mechanism for the reaction that's happening over here. There's an NO2 getting attached to it, so you have to show what the intermediate is.
NO2 plus उसके पास
Na2 और H एक साथ होंगे फिर एक वो positive.
हाँ, ठीक है. So it's just going to be that there's going to be NO2 over here, and there's also going to be H over here, and the benzene.
अंदर arrow जा रहा होगा, curly arrow.
ठीक है, and the next step is the H will be giving back towards the ring. It's going to give back the electron. Or should maybe draw color. It's although that's I don't think they're asking for it, but that's the first step. So then you have write an equation to show how the H2SO4 catalyst is reformed. So how is it reformed?
HSO4 minus plus H plus, so H2SO4 formed.
Okay, this H2SO4, huh? So when the H leaves, but for H, when the H leaves, where does it go? It is grabbed by the HSO4 minus 1. So the HSO4 minus 1 ends up accepting that H plus 1 to form H2SO4 back again. As a step 2, suggest the reagents and conditions for and name the type of reaction for step number 2. What is step number 2? Again, it's NO2 turning into
10 plus concentrated HCl. Concentrated HCl.
Concentrated, reduction, that's reduction. So then, right, we did that.
Reduction. Can we add LiAl BR4 as well?
इसका जो है ना, this is specifically 10 plus concentrated HCl. That's it.
Okay, sir.
ठीक है. वो explain कर देता हूँ. Okay, remember where is LiLH4 used? Reduction of nitriles. That's where it's used. When you have CH3CN, that gets reduced into an amine by LiLH4. So where else is it used? It's used in amides. Amides are reduced using LiLH4, but not this one. Okay, nitrobenzenes are reduced with 10 plus concentrated HCl. That's it. Let's have next one. Okay, what's the next question? We've got. Did you use the? You'll probably get a question on molecular formula of this acid. So all you have to worry about is counting the carbon atoms, and the hydrogen atom. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
C15.
And 3 other carbon atoms. So C15 and the hydrogen atoms. That's 1, 2. Remember, benzene carbon atom only makes 3 bonds.
15.
There's 1, 2, 3.
H15.
Or can't be. There's one over here as well. Confirm a 15. That's 3, 6, 9, 10, 11, 12, 13, 14, and there's one over here. That's 15. And then you've got
an N.
two oxygens and one N. Name the functional group apart from what is this functional group and what is this functional group?
Carboxylic and amine.
Carboxylic and amine.
Okay. Or calculate the maximum mass as a moles का question.
Alkyl भी कह सकते हैं as a functional group.
Arenes?
Alkyl chain.
I doubt they would give you marks for that. But it's apart from benzene, it's just a 1 mark question. So you just I should calculate. Forget this. This one. So the position of this. This is again. It's the same carbocation stability question. Okay, you get a lot of this question. Which carbocation is more stable? The one that is bonded to more carbon chains or less carbon chains?
More carbon chains.
Okay, so more carbon chains. So when you have a tertiary carbocation or a 3-degree carbocation, it is going to be more stable. Why? Because its electron density would be lesser. Okay, because of the electron donating effect. So the question is, the position of the substitution and the electrophilic substitution of arenes can be explained based on the stability of the intermediate cations formed. Okay, so he's talking about the stability of the carbocation. So use this information and your knowledge about the stability of cations to suggest why the CH3 group directs incoming electrophiles to the 2 and 4 positions. So first thing, look at this carbon atom. Is this a tertiary, secondary, or a primary carbocation? What type of carbocation is this?
So
secondary?
Tertiary.
Tertiary. It's got a carbon chain on this side, top side as well. So it's a 3-degree carbocation. It's a tertiary carbocation. So it's going to be more stable, right? And
सर तो इसका electron donating effect ज़्यादा होगा?
हाँ, क्योंकि it's got carbon chains on all sides, right?
More than 2 degree मेरे ख्याल से.
हाँ, मतलब हर side पे carbon chain, so it's going to have an electron donating effect. The positive charge density is going to be very less. So which is why it's going to be very stable. So what about this one? Is this EBK? This is
also
right?
tertiary. Yes.
So this one is also 3-degree carbocation. And what about this one? This is a
secondary.
So there are only 2 carbon chains, one on this side, one on this side, right?
एक H होगा ना इसके साथ.
हाँ, एक H है.
So you only have 2 carbon chains. So this is the one that's unstable. So you're just going to mention this. It's just going to be a simple answer. It's just 2 marks. Okay, you're going to talk about this being a 3-degree carbocation and this being a 3-degree carbocation. So you're going to say, okay, there are alkyl chains have electron donating effects, and that makes the carbocation stable. This is a 2-degree carbocation, so it has fewer alkyl chains or carbon chains around it. So there's going to be less electron donating effect. So this is so a question. Let me just do one question. We've got winter 21.
बहुत आसान है सर.
कौन सा?
ये वाला बहुत
ये हो जाएगा सर.
सर नहीं सर करा दे सर, मुझे थोड़ी सी मुश्किल है.
सर बहुत आसान है.
एक सेकंड चुप करो ना थोड़ी देर. क्या मैं कौन सा कराने मैंने?
वो रेट डिटरमिनिंग स्टेप वाला जो आपने अभी खोला हुआ था, बस
ये वाला.
यस सर.
तो पहले ये वाला करो. एक सेकंड, एक क्वेश्चन था. जस्ट 1 सेकंड. 2142 question 1. Yeah, I think we already did this. चलो ये म्यूट ही कर लो. अच्छा वैसे बता दो कोई क्वेश्चंस है और के ये करने.
सर ऑर्गेनिक तो ठीक है, अब काफी हद तक इजी लग रहा है, थैंक यू फॉर दैट. लेकिन ज्यादा मेन इश्यूज किधर आ रहे हैं सर मुझे? केपी और के वाले आते हैं ना सर क्वेश्चंस, उनके मिक्स क्वेश्चंस आते हैं, मोल्स के भी आते हैं और केपी के भी आते हैं, वो थोड़े से मुश्किल लग रहे हैं.
के डिसोसिएशन कांस्टेंट के कर लेते हैं, जस्ट 1 सेकंड.
हाँ
यस वो प्रवास है
कांस्टेंट वाला, और थोड़े बहुत वो लाइगेंड्स वाले जो क्वेश्चंस आते हैं ना ट्रांजिशन मेटल्स के अंदर, उनमें भी थोड़ी सी इश्यूज हो रही है.
केस टैब वाले
ड्रॉ करने
अच्छा एक से मैं पहले एक कर लूं, फिर वही कर लेता हूं. I'll open that. ठीक है, क्वेश्चन नंबर 1 पार्ट E, just 1 second. State two major factors that affect the numerical magnitude of 1 second. Is this E part, question 1 part E, that affect the magnitude of the lattice energy? That's charge density, right?
Ionic radius.
Okay, so charge density is basically composed of two things. One is the charge. You greater the charge, the stronger the lattice, right? And it's inversely proportional to the ionic radius. Bigger the ion, the weaker would be the attraction. So we're now going to try and do questions related to.
सर यही वाला कर लें.
से मैं बोल रहा हूँ ये इक्विलिब्रियम, राइट? So hold on 1 second. I said this one. As for each factor separately. As this part, sorry, part 2. Let me just go through part 2. So he's comparing NaCl and he's comparing it with radium sulfide, right? So he's saying whether it makes it more exothermic, tends to make the lattice energy most for each factor separately. First thing, charge.
Sir, एक question है इसके. Question has नहीं इसी से related ये. इसके अंदर question has not like stated कि using the data booklet explain this answer. लेकिन इसके अंदर you can look at the data booklet and ionic radii से देख के आप बता सकते हो, उसका आंसर दे सकते हो. लेकिन अगर नहीं होगी अब data booklet, तो how would we answer this?
You can at least make some guesses. Like radium is obviously a very big ion, right?
Yes.
Because it's got more shells. So.
जी.
So you can, but you at least know the trends, kid. Like by looking at the position of the atom in the periodic table, you can figure out whether it's going to be big or small, right? Achha, but this question, achha, let me separately. First thing separately, charge. According to the charge, this one has greater charge, so its lattice energy is going to be, it's going to be more exothermic, right?
Yes.
And the second part is about the size of the ion. So whose ions have bigger size? It's this one. So when you have so the problem is when you have bigger ions, because radium is clearly bigger in size, and if you compare Cl -1 and sulfur -2 as well, sulfur is bigger in size. Remember that. They're both isoelectronic. This has 18 electrons. Sulfur also has 18 electrons, but sulfur has fewer protons. So that means sulfur has a weaker attraction for its electrons. So the size of the sulfur ion is bigger in size compared to Cl ions. So in both cases, the positive and the negative ions, radium sulfide has bigger ions. When you have bigger ions, that indicates that it's going to be a weaker lattice. So it's going to be less exothermic. So Isha, the point is, you can discuss these two things separately, but you can't combine them together, because one of the factors saying that one of them is more exothermic or makes it more exothermic. The other one is stating that the other one, this factor makes it less exothermic. So unless we have values, we can't really tell whether overall it's going to be more exothermic or less exothermic. Okay, Isha, is that point clear? And because in the next part, they're actually looking for the dominant factor. So if this is a bigger value, or this has a bigger effect, then the whole radium sulfide lattice would become more exothermic.
Sir, they've asked in the second part, they've asked if for each factor you have identified in E1, do we have to discuss both of the factors like charge and the size?
But separately. At the moment over here, they're asking you to discuss it separately.
But wouldn't that contradict the entire statement?
For each factor you have identified, state whether it tends to make the lattice energy of radium sulfide more or less exothermic than that of sodium chloride. So
एक more करिए, एक less करिए.
So the point is, okay, we can't really figure out in this case. Okay, that's a pehla point. As a pehla point, okay, you can't. They're asking you to discuss separately. Okay, what will charge do? You got a greater charge, so it's going to be more exothermic. It's going to be a stronger lattice. The other one, the size of the ion, this has bigger ions, so it's going to be a weaker lattice. Okay, so separately, one of them is making it more exothermic, the other one is making it less exothermic. So we can't state whether overall effect is going to be more exothermic or less exothermic. I mean, they're kind of canceling each other out. But in the next part, he's now asking you to identify the dominant factor. Now he's asking which one is going to have a bigger effect. So when you look at the enthalpy change of radium sulfide, you would notice that it is more exothermic compared to sodium chloride. So if it is more exothermic, that means charge is a more dominant factor. Is that point clear?
More exothermic, इसलिए हम इसको ले रहे हैं.
क्योंकि one of them was stating that it's going to be more exothermic, the other one was stating that it was going to be less exothermic. So combined, we didn't know, okay, what would be the overall effect, but they gave us the values. And when we looked at the values, we figured out that RAS is more exothermic. So that means the more exothermic factor is more dominant, right? Is that clear?
जी.
Let me check the MS 1 second. Which paper is this?
सर एक चीज मैं कंफ्यूज करी है, चार्ज डेंसिटी भी रेडियस पे रिलेट नहीं करती कि जितना छोटा रेडियस हो
नहीं वही था ना कि स्टार्ट पे ना इट्स चार्ज डेंसिटी इज द सेम थिंग. इट्स लेकिन उसका कहता है चार्ज डेंसिटी इज मेड अप ऑफ टू फैक्टर्स, वन इज चार्ज एंड द अदर वन इज इनवर्सली प्रोपोर्शनल टू आयनिक रेडियस. तो basically the question is about charge density, but he's talking about the two factors separately. ठीक है, is that clear?
Yes, sir.
As I say, let me just open the MS for this one. That's exactly what we stated as well. Like, not sure where the paper is. So I told you that the charge is the dominant factor. That's exactly what the marking scheme is also saying. So what's next? Does anyone have any other questions?
सर इसका अगला पार्ट भी आगे.
Part E2. Sorry, just a second. Part. Size tends to make the less exothermic, so that's exactly what we said. And charge tends to make that is definitely incorrect. I mean that makes the marking scheme is incorrect, definitely incorrect. I mean, one of them is making it less exothermic. The other one, ये वाला part, that I think that's a typing error.
सर एक सवाल पूछना था.
Okay, if it's more highly charged, it's going to be more exothermic. ठीक है, that's definitely a typing error. हाँ जी, क्या सवाल है?
सर कभी कभार वो कहते हैं कि आपका जितना पोलराइजेशन का भी आता है इसमें कि आयन को डिस्टर्ब कर देता है अगर आपका चार्ज जितना बड़ा हो या इस तरह कुछ, वो आप समझा सकते हैं इसी इक्वेशन से?
चार्ज डेंसिटी से?
नहीं, वो
that question
पोलराइजेशन का मेंशन किया
हाँ,
होता है.
that question is about stability of carbonate ions, right? That's a completely separate question. उसके अंदर if you have a smaller ion, like it's about group 2, ठीक है, they usually ask about group 2 ions. So if you have a smaller ion has a much stronger charge density. It's got a much stronger attraction for electrons. So what happens is that the carbonate ion becomes unstable. The oxygen in the carbonate breaks off, taking electrons with it, ends up forming MgO. Let's say this is Mg. And the carbonate ion decomposes. So the smaller the ion, the greater is the charge density, the stronger is the attraction for electrons. That makes the carbonate ion very polarized, or the magnesium ion polarizes the carbonate ion. So it makes it easier to decompose. Vice versa, if you had a bigger ion, that would do this. That will not pull the oxygen away from it. Okay, is that point clear?
Yes, sir.
As in, I just told you, this part is definitely, this should have been more. Okay, there's definitely a typing error here. Part E2. Okay, if it's more highly charged, it's going to be more exothermic. Okay, that's definitely a typing error in the MS. And they even negated that they told us that the dominant factor is the charge because lattice energy was more exothermic. So, I mean, this is definitely more, okay, not less. अच्छा, इसके बात करो आप.
जी sir. Why the value calculated is less than 6.7?
अच्छा, this one is ethoxy ethane can dissolve both in water, and so this is the solute. Again, this is about KPC, so it's the expression and numerical value for the partition coefficient between water and octane 1-ol are given. Water and octane 1-ol are immiscible in an experiment. So there are two layers, octane 1-ol and water, and some of the, I mean, this solute is dissolving in both layers. In an experiment, octane 1-ol 20 is added to a solution of ethoxy ethane in water at 20 centigrade. The mixture is analyzed immediately and a value of KPC is calculated. The calculation is performed correctly. The value calculated is 5.625. Explain why the value calculated is less than 6.760. So what is happening in an experiment? To ethoxy.
Sir, उसके H2 में concentration कम है. उसकी H2 में concentration ज़्यादा है.
नहीं, I'll explain why it's less than. It's not because remember KPC is a constant. All equilibrium constants, they only change with temperature, right? So the first point is, are they changing temperature? They're not changing temperature, right? So that means KPC must be constant. Is that clear? I mean, it should be constant. Like if it's coming out to be 6.760, so no matter what type of concentration there is present, right? It's got to be constant. The ratio and whatever the layer is, as long as it's an octane 1-ol layer, no matter what the volume is, no matter what the volume of water is, the ratio would always come out to be constant. Okay? So it only changes with temperature. So the problem is, why is the value less than 6.760? It's less than 6.760 because the mixture is analyzed immediately. That means the equilibrium has not been reached. This is what's happening. You had you had water, right? And there was ethoxyethane in water, right? And what you did was that you added a solution of you added in an experiment, octane 1-ol is added. So you started adding octane 1-ol from the top. Now it's going to take some time for the equilibrium to reach. Some of the X would start leaving, but it's going to take time. So if you immediately analyze the results, there's obviously going to be more concentration of X in water and less concentration of X in octane 1-ol because the equilibrium has not been reached. The equilibrium constant Kpc can only be calculated if the mixture is already at equilibrium. So that's the error that you're making. You shouldn't have done it immediately.
Yes, sir. Makes sense.
So Baki, the rest is the same. I said, let me just do one more question. We've got Specimen 2022. 1 second. So question 8 part B. Okay, ibuprofen contains a chiral center and has two enantiomer state, one similarity and one difference in the physical and chemical properties between the two enantiomers. Enantiomers are basically your mirrored versions, right? So what are the two differences between the two enantiomers? Similarity is that they have almost the same physical and chemical properties.
One of the difference will be one of the isomer will work and one won't.
Okay, so the biological activity would be different. Or what you can also state one difference, state one similarity, one difference. So the biological activity or functionality of the molecule will be different because that's very shape specific. Okay, one of them will bind with the active site, the other one will not be able to fit with the active site. The other difference is that they both rotate plane polarized monochromatic light.
सर मेरे ख्याल से 1 मार्क के लिए काफी है.
Oh, sorry, there's a plane polarized monochromatic light in different directions. Is rotated in different directions.
सिर्फ वैसे enantiomers होते क्या?
Optical isomers.
सर वो आपने वो कोप्लेनर वाला क्वेश्चन भी समझाना था.
अच्छा वो मैं करता हूँ. कौन सा क्वेश्चन था?
I sent on the group.
So ये part 2 क्या है?
नहीं एक सेकंड पहले मैं explain कर दूँ कि अच्छा remember कि you in ACE you studied enantiomers, right? You studied mirrored images. Now I'll explain the synthesis part because there are very few questions on this, so it's important that you should know this. I said these are enantiomers, right? Mirrored versions. This is chiral carbon, this is chiral carbon. Remember, the physical and chemical properties are very identical, but biological activity is going to be different because of the shape. It's just like your hands. If you have a glove for a right hand, only your right hand can fit into it. Your left hand will not be able to fit into that glove. So enzymes work in the same way. So functionality, biological, that's different. This thing you just have to memorize that the physical difference between the two is a physical test that you can do is that they rotate plane polarized monochromatic light in different directions. What is a Racemic mixture? It's a mixture of two enantiomers. So when you have in a solution, when you have both of them, so it's a mixture of both enantiomers. Okay, and I'll just open the marking scheme for this as well, just to check the wording of this.
There must be equal.
Okay, so the wording for this is going to be a mixture containing equal amounts of each enantiomer. So I think you should write equal amounts of each enantiomer. Physical and chemical properties are almost the same. Biological activity is different. And the ability to rotate plane polarized monochromatic light, that's another one. This one you just memorized, TK, that's it. Even this one, Racemic Mixture, nothing was going to be asked. Just know that a Racemic Mixture is having both enantiomers. So one thing else that needs to be known is about organic synthesis. What type of chirality will happen, or what type of optical isomers will the molecule form? So in that case, especially related to mechanisms. So for example, if you talk about, so I'll just briefly give an overview of this. If you talk about nucleophilic addition, what happens in nucleophilic addition? This is the mechanism that you got aldehydes and ketones. Carbon is positive. I'll just draw the mechanism quickly. There's a CN-1 that comes in, which attacks this carbon atom. And as a result, in the middle, you form the double bond electrons, they accumulate at the top, right? And the CN bonds at the bottom, and there's an H. And in the next step, the H+1 joins in. And you form cyanohydrins. So that is nucleophilic addition of aldehyde and ketones. Now, one thing about chirality is that if you look at the shape of this molecule over here, specifically if you look at this carbon atom over here, this is trigonal planar. So the carbon kind of looks something like this. It's got a double bond. It's fan shaped, right? It's got an H, and it's got a CH3 as well, right? So the carbon is like this. The oxygen over here is negative. This carbon is positive. So what type of chirality will be formed over here? It's forming a chiral carbon over here. So what type of chirality will happen? The CN-1 is interested in this carbon, which is positive. If it's interested in this carbon that's positive, then the CN-1, remember, it's a flat planar molecule. It's like a fan-shaped molecule and a carbon in the center. So the CN-1 can attack from the top, or it's got another choice. The CN-1 can come and bond from the bottom as well. In both cases, you're going to form, if it comes from the top, then what will happen is that all the other bonds of this carbon, the CH3, they'll be pushed downwards. The H is going to get pushed downwards, and the O will also get pushed downwards. So that is one type of chiral carbon that's going to be obtained. Vice versa, if the CN attacks from the bottom up, then it's going to look like this. The CN will bond at the bottom, and all the bonds are going to be pushed in the upward direction. So the CH3 gets pushed upwards, the H also gets pushed upwards, and the O also gets, you get both kinds of mirrored images for this one. So what's happening here is, remember that whenever you have a trigonal planar arrangement, the intermediate or the starting point is a trigonal planar arrangement. You'll get both types of chiral carbon atoms. Why? Because the CN could attack from the top. It could also attack from the bottom as well. So both types of mirrored versions can be formed. Is that clear?
Yes, sir.
If you have, you won't get a big question on this. It's just going to be a very small question. So they'll ask you, okay, why in this mechanism are you getting both chiral carbon atoms, or both? Why are you getting a Racemic mixture? Why are you getting a mixture with equal portion of both enantiomers? And so the only 2-mark line that you have to, or probably a 1-mark answer for this would be,
Electrophile can attack from both sides.
It's first thing, it's trigonal planar. The molecule is trigonal planar, and the Cn-1 could attack from the top or it could attack from the bottom as well. I'll do another one similar to this. Okay, they might ask you about this as well. Okay, if you have let's say there's a secondary halogenoalkane. Okay, C2H5, and there is H and there's Cl. And the mechanism is SN2, in which let's say there's an OH minus 1 coming in, and there's a carbon which is positive and the Cl which is negative, and it attacks and the Cl leaves, right? In this case, they're saying that it doesn't form a racemic mixture. You get always one type of chirality, which is just one version of the molecule. You don't get a racemic mixture. The OH replaces the Cl. So the answer to that is the OH minus 1 will not attack from two sides. Why? Because if I draw the
repulsion,
because if the Cl is negative, the OH minus 1 would always attack from one side. It's not going to happen like this in the previous case where the Cn minus 1 could attack from the top. It would also attack from the bottom. Over here, the nucleophile is always going to attack from the left side if the Cl is on the right side. So it's always going to attack from the left side, which is why you will always get one type of chirality. It's always going to attach from one side. Okay.
In the chlorine side, so.
So, any other questions?
What about it?
sir वो co-planar वाला जो मैंने किस पे भेजा
ठीक है मुझे वो नहीं क्या था कैसे बताना एक सेकंड पहले मैं co-planar वाला we've got one question okay which paper is this
I sent on the group मुझे because I found it in topical उसका number नहीं मुझे याद
वैसे सर्च कर लेते हैं 9701 co-planar PDF Yeah, no, there's a question, but अच्छा एक से मैं ग्रुप पे देख लूं I'm not finding the question, but I'll just explain TK very quickly. Not really. I mean, the question was something like this: you had
question says that all carbon atoms in benzene lie in the same plane. This means they are coplanar, but not in the case with cyclohexane.
No, the question was, okay, let's say they talk about butane, right? TK, if I remember this correctly, so the question is, can all carbons in butane, can they be coplanar or not? Which means that can they lie in the same plane or not? So the answer to that is, remember carbon over here is going to be tetrahedral. So when something is tetrahedral, then remember that two of the bonds are always in the same plane. Whatever the shape of a molecule, two bonds are always in the same plane. Okay, so this bond over here and this bond, this is the bond that's coming out of the page towards you, and this is the dotted line that's going into the page. Is that clear? So if this is the first carbon atom, and this is the next carbon atom, that's also tetrahedral, right? So if it's tetrahedral, then one bond would be coming out of the page, one would be going into the page, and one would be in the same plane, right? And here's another carbon atom next door, so that's
So this can't be coplanar.
It can be possibly coplanar.
What does coplanar mean, sir?
Okay,
Lying in the same plane?
Lying in the same plane. No? Remember, okay, if this is tetrahedral, these two bonds are lying in the same plane, right? Is that clear?
Yes.
And this is the next tetrahedral. Okay? So these two bonds are lying in the same plane, right?
Ji.
So agla wala carbon hai that these two bonds are lying in the same plane. So all 4 carbon atoms are actually lying in the same plane.
We have to see the carbon atoms only.
The question, the one that you asked was about carbon atoms only. Okay? So that is a possibility because remember, around a sigma bond, rotation is possible. So that means that this CH3, I mean, it's attached like a fan. Think of it as a fan. So this thing can sort of rotate. I mean, you can sort of spin it on top. I mean, think of this carbon atom as 3 bonds that are coming out of it. Okay? So this thing on the top can spin around as well. So it's not always that this bond is in the same plane as this one. Do you get my point? Again, there's a possibility that it can be. Is that clear?
Sir, please transition वाली करा सकते हैं? Sir, any 2 transition questions?
ठीक है, मैं कर लेता हूँ. तो ये clear है कि whenever you have any molecule, if let's say I had another question, I had a molecule with 3 carbon atoms, right? So can this and you had all these hydrogen atoms next to it, can all 4 can they be coplanar or not? That is not possible. In this case, it's not possible.
तो ये बात समझ नहीं आई.
वो मैं explain इधर करता हूँ ना कि ये वाला जो है ना, this is all 4 carbon atoms. Focus on the carbon atoms. They can't be coplanar. Why? Because if I focus on this carbon atom, okay, this carbon atom is tetrahedral, right? So that means it's got 1 bond over here, 1 over here. 2 of the bonds can be in the same plane. 1 bond is coming out of the plane and 1 of them is going into the plane, right? You clear? So I've got 3 carbons attached to it. So I can have 1 carbon in the same plane. I got to have the second one in the same plane, but the third one, if it's a tetrahedral shape, will be out of the plane. इसके साथ कितने carbons are? That's 3 carbons, right? So I can never have the third one. The fourth one is a hydrogen atom. और फिर वो बाकी सारे H हैं, ठीक है? It's got H atoms attached to it. Not interested in those H atoms. But the point I'm trying to make is, in this molecule, all 4 carbon atoms can never be coplanar. Okay, because in a tetrahedral shape, 2 of the bonds can be in the same plane, but the third one will not be in the same plane. Do you get the point?
No.
इसको visualize करो ना कि tetrahedral shape है ना? In a tetrahedral shape,
you're trying to say that the upper wala carbon is going to make its hydrogen bonds या जो भी bonds उसके साथ
hydrogen को
होंगे.
छोड़ो, hydrogen को तुम focus नहीं कर रहे. Imagine ये page जो है ना, this is the plane, right? ठीक है? How do you make a tetrahedral shape? When you have a tetrahedral shape, 2 of the bonds are always in the same plane. So when you have any shape, ठीक है, कोई भी shape कर लो, even when it's any 2 random bonds, those 2 bonds are always in the same plane. मतलब 2 pencils, pick 2 pencils, ठीक है, उनको आप इस तरह रख दो, ठीक है, they can lie flat on a plane, right? Is that clear?
Yes.
The problem comes about when you have a third bond, right? If it's a fan shaped, the third one can be put in the same plane as well. Like if there's a third pencil, you can put it in the same flat plane, right? Is that clear?
Yes.
Similarly, when you have a tetrahedral shape, the two bonds. You have a pencil over here. You got put one pencil over here. That's an 109.5 degree angle, right? But the tetrahedral shape is a three-dimensional shape. So one of the bond is going to be coming out of the plane towards you. Is that clear?
So that bond is not going to be coplanar. That's going to be in another plane.
So the problem with the tetrahedral shape is two bonds can be in the same plane, but not the third one. ठीक है? ये जो trigonal planar shape है ना, इसके अंदर all three bonds can be in the same plane.
But not the fourth one.
Trigonal planar, but there is no fourth bond, right? But other ones as well.
So benzene is going to be coplanar. Cyclohexane is going to be coplanar as well.
The cyclohexane cannot be coplanar. Cyclohexane mein all 6 carbon atoms are connected in a ring in a tetrahedral arrangement.
The question just जो I sent उसमें था 3 benzene attached एक साथ और एक benzene और एक cyclo. हाँ, एक benzene और एक cyclohexane attached एक साथ.
So this is what cyclohexane would look like. It's going to be the carbon atoms at least will not be coplanar.
ठीक है.
Because it's one tetrahedral connected to another tetrahedral connected to another, so it's going to be up and down. It's not going to be at least the carbon atoms. These are black liner. That's carbon atoms. Then they won't be connected in the same plane. ठीक है, is that clear?
सर मैंने आपको पिक्चर भेजी है उस क्वेश्चन की. उसमें आखिरी के जो 3 है C, D and E वाले स्ट्रक्चर्स वो समझा दें. A और B समझ आ गया. व्हाट्सएप पे मैंने भेजा.
C, D and E, right? C is. It's hard to explain over here, but I'll try. C is like this. Okay, it's just 1 second. The C is, remember, it's got a CST. It's got, so let's focus on this C over here. So what did I tell you about the tetrahedral shape? Okay. Carbon is making 4 bonds, right?
3 bonds will be coplanar, but the 4th bond will not be coplanar.
The 3rd and 4th one will not be coplanar. Okay, there's going to be a dotted line. In a tetrahedral shape, 2 bonds will be coplanar, not the 3rd one or the 4th one. So I've got a CST. I've got a CST. These can be coplanar, right?
Yes.
And I've got another carbon atom, and that's also tetrahedral. So this other carbon atom, 1 second, is also CST and CST. They can be coplanar, right? And it's got oxygen atoms attached to it. I said we don't care about the oxygen atoms. I said think about the shape. You've put the molecule flat on a table, right? You got a CST, a carbon, and a CST. Then you got a bond going into the page that's connected to an oxygen, and you got a bond that's coming out of the page and that's connected to another oxygen. Then you have another carbon atom that's also lying flat on the table. You got 2 CSTs. The 3rd bond is going into the page, and the 4th one is coming out of the page. But other carbon atoms are all lying on the lying flat on the plane. They are. Okay, so this one is. So all the carbon atoms at least, these carbon atoms at least they're all coplanar. The same probably applies to E as well. If you have benzene, that is coplanar by default because it's trigonal planar, right? Then you have this carbon atom. So that is also in the same plane because this carbon atom. They're not even talking about the oxygen, so I don't care about the oxygen or the NH2. Like up till this point, it's going to be planar, right? Because it's 3 carbon atoms, 3 bonds. trigonal planar, so this carbon will be in the same plane, right? And over here, I've got another carbon atom that's going to be in the same plane as well. And after that, it's going to be tetrahedral, right? And even in the tetrahedral shape, one of the bond would be the same plane. So I can put a CH3 over here. So that is a possibility that all carbons can be in the same plane. The NO2 and the H can go in and out of the plane.
So yeah.
So, but the carbons can be in the same plane.
Okay. And the D. CH3CHOH. That's also coplanar.
C, C, and C double bond O and OH, right?
Yeah.
And there's an OH, I think, over here.
There's one tetrahedral.
Just one second.
Two tetrahedrals.
So there's a CH3 over here. Anyways, I'm just focusing on this carbon atom. The carbon atom will be tetrahedral, right?
Yes.
So this carbon atom is connected to a carbon on one side and a carbon on the other side. So there's a carbon. I'm going to keep the two carbons in the same plane. This one is double bond OH, and that one is C with CHs, right? So are the carbons in the same plane?
Yes.
Okay, the H and the OH could be out of the plane. The H could be going into the page and the OH could be going out of the page. Okay? So just remember that in the tetrahedral shape, two of the bonds could be in the same plane. Or it's not necessary that they are in the same plane. They're saying, can they, the question is, can they be in the same plane? So they can possibly be in the same plane.
Even if in a position किसी और तरीके से लगा के we can orient it.
You can sort of change it and twist it around, okay? So you can make them coplanar, okay?
Okay, I get it. Thank you.
So Isha, electron affinity, if you have more shielding, then it's going to be harder to remember. Electron affinity is the same as electronegativity. It's the same factors. If something is more shielded, it's not going to attract electrons. So the electron affinity will decrease. It will become less exothermic. Yes, so repulsion. So it's going to be a lot harder to actually attract electrons. So it's going to become endothermic actually. Not endothermic, but it's going to be less exothermic. And always remember the first electron affinity is exothermic. After that, it becomes a negative ion. So it becomes harder to gain electrons. तो ठीक है और क्या करना था वो क्या था ट्रांजिशन मेटल किसने कहा था
सर एक ट्रांजिशन मेटल का लाइक क्वेश्चन था जिसके अंदर copper with H2O6 combines with H2O2. What does that do?
Yeah, I don't know. It's not in the syllabus. It must be, I mean, the answer would be part of the question.
The answer was redox reaction. It's a redox reaction.
There was one question where you had copper. So the oxidation state would be changing. So that is why it's going to be an redox reaction. It would be. The answer would be part of the question. Like they would state it. Okay, it's. So question bhejo ke pata lage. It's. Whether it was were you supposed to use electrochemistry or what?
सर
हाँ जी
सर ये कॉपर और क्रोमियम का जो आइटम होता है इसमें जो 4s शेल है उसमें एक इलेक्ट्रॉन होता है इसकी कोई खास वजह है
नहीं बस वो ज्यादा स्टेबल इलेक्ट्रॉनिक कॉन्फ़िगरेशन है no one is going to ask you what's the reason for that
ठीक है
and I guess it was an electrochemistry question. चलो ठीक है if there is no question so I think it's getting late. बस वो देख लो end में कि just make sure the parts where you have to memorize stuff go through the transition metal notes go through organic वो spider chart notes, ठीक है, that's एक सेकंड solubility exo होगी तो solubility, I'll just give you a quick recap on solubility, ठीक है. There's going to be a typical question that is most likely going to come in your exam, ठीक है, tomorrow as well, and that is के कहाँ पे लिखूँ, एक second, is there space? This one. Remember, they're going to talk about the solubility of hydroxides, what happens to it down the group. So it becomes more soluble, right? So if I have magnesium hydroxide, it's going to dissolve. And when it dissolves, it turns into magnesium ions, aqueous, and 2 OH ions, aqueous. And this is known as enthalpy of solution. And the enthalpy of solution is made up of two parts. The first thing is you break the lattice. That's the negative of lattice energy. That's an endothermic process. You break the lattice. You break the lattice into its ions. And once those gaseous ions are produced, they surround themselves with water and they form aqueous ions. That's the enthalpy change of hydration. And that's your exothermic part. So one of the parts is endo, the other one is exo. So what happens down the group? Enthalpy of solution. So down the group, the solubility increases. So the solubility of your hydroxides it increases. That's the first part. Barium hydroxide is more soluble. So if it increases, that means enthalpy of solution becomes more exothermic. The more exothermic, the more feasible it is, the more the less energy it is needed for the reaction to happen. So enthalpy of solution becomes more exothermic. So why is it becoming more exothermic? The reason why it's becoming more exothermic is that down the group, ionic radius increases, sorry. So when you have bigger ion, the bonds that are broken are going to be weaker, and the bonds that are formed are also going to be weaker. So it's going to form, you need to break weaker bonds in the lattice, and you are going to form weaker bonds with the water molecules as well. So down the group, ionic radius increases. So both delta H hydration and lattice energy, they decrease. And since they both decrease, but we've already stated that the enthalpy of solution becomes more exothermic. So the exothermic part decreases less. It's a relatively bigger, and the endothermic part decreases more. So the last part of the answer would be part delta H. Hydration decreases. Less compared to lattice energy. So this is a typical 3 or 4 mark question that comes very often. So make sure you remember that what happens to hydroxides, that they become more soluble, which means that the enthalpy of solution becomes more exothermic. Down the group, the ionic radius increases. So both of these values will decrease. But since it's becoming more exothermic, so this is relatively bigger compared to this one, or you can say that this decreases less compared to this one. Hydration is always exo because you're forming bonds with water. I mean, this part is always exo. You're forming bonds with water.
So lattice energy is also always exo.
Over here, you're breaking the lattice. It's the negative of lattice energy. So it's actually you're breaking the lattice, right? So which is why it's going to be endo. I mean, in this case, it's going to be endo, TK, because you're going in the opposite direction. TK. Lattice energy is exo, but lattice energy is gaseous ions combining to form the lattice. We're doing the opposite over here. We're breaking the lattice. Okay? Yes, exactly. The direction is the opposite because of the sign. Just go through last name, just go through inorganic and just memorize, focus on the stuff that you just need to memorize, TK. Organic and inorganic.
Okay.
And also remember one thing, one tip about the question. There's going to be at least one question which would be extremely hard. So focus on the other 9 questions, leave that till the end. Don't panic with that difficult question. There's at least going to be one or at times 2 questions that will be very hard. Okay, focus on the other 8 questions. You can just first initially focus on the other 8 questions. Like if it's the first question that's very hard, I mean, just ignore that. Try and do the rest of the questions, then come back, save time and come back to that question at the end. Okay.
Okay, sir. Thank you.
Thank you.
Hafiz.
Thank you so much.
सर मोल्स के क्वेश्चन काफी कंफ्यूजिंग होते हैं, उसके लिए कोई टिप देंगे?
इसमें एक तो there's lesser chances. I mean, you won't get a big question on moles most likely. ठीक है? Even if I go through this entire question, the confusing part would be that if, remember, there's at least going to be 2 questions that are going to be hard, very hard. Okay, so it depends what type of moles questions do you get. There's no tip for that. The only tip for moles questions is that make sure you sketch it out. Okay, what's happening? Okay, that would, because the difference between AS moles questions and the A2 moles question is, okay, in AS they would break it down into smaller problems, right? In A2 they just give the whole question and there's no steps to it. Okay, they just give you a 4-mark question, that's it, and you just have to figure out all the steps yourself. So it's it would be a lot easier if you just sketch whatever is happening. Okay, if they're adding 100 cm, I mean, यहाँ पे देखा होगा, whenever I solve a question, I start sketching things. Okay, that makes more sense. So try and sketch it out. Okay, what's happening, because they won't give you steps now. Okay, they'll just give you the whole question and try to solve 4 or 5 steps in just one step. Okay.
Okay, sir. Thank you.
Okay.
Love it.